My roll number is H5. Today my topic is designing technology co-optimization trades-off for building the best processor. The concept of designing technology co-optimization, in shortcut we used as DTCO, has existed for long time in the semiconductor industry. However, with a move to smaller, more complex process nodes and the manufacturing of chip design primarily in foundries, the need for a structured relationship for a co-optimization sorry. However, with the move to smaller, more complex process nodes and the manufacturing of chip design primarily in foundries, the need for a structured relationship for co-optimization has become even more essential. Early stages, the f- early stages, the first reference to D2CO designing technology co-optimization using Google search occurred in 2005. The graph in figure illustrates the increasing in the number of references related to DTCO in recent years based on search result. Published paper illustrate a wide varieties of related topics such as the DTCO process definition as well as a specific design areas including the standard cell library, block inline and static random process. As illustrated by the published example, DTCO can encompass a wide variety of topics. In addition to such specific subject, DTCO can take different forms depending on the process and designing timelines, especially during long cycle when designing work is taking place and concurrently with the with the process and designing timeline, especially during the long cycle designing work is taking place concurrently with process development. Experiment often can be done on a previous technology node to understand a design sensitivity to different technology options. Early interaction with the foundry to comprehend a new technology capability and limitation is another key to determining how, how to optimize a design. And finally can analyze the technology digital object identifier, date of current visor, trade-off building for the best process. Fundamental technology scaling is not keeping pace with more and law and other designing options are necessary to continue with the historical trend. The significant amount of data that exists for a design based on a previous technology offer the advantage of providing a converged design and a variety of design type. Often our integer and floating point data paths will have different designing characteristics compared to the instruction and data caches as well as the decoding and scheduling units. Some example of those differences include the existence or lack of SRAM arrays, aspect ratio, number of repeaters, upper level metal usage, and overall cell utilization. Gathering data across all of the converged design can provide valuable insight that one are more difficult to get when ramping up a new processor technology. A small designing is initially used to verify that the PDK electronic designing automation tools and overall environment work correctly. In addition, it can be used for many quick iteration and experiment. Once confidence the initial results confirmed, a large design or a design can be employed to assess the technology capabilities. Fundamental technology scaling is not keeping pace with Moore's law. and the other designing options are necessary to continue with the historical trend. Each of the areas require a tight collaboration between the technology and design to achieve an optimal product. One of the concern for high performance design moving forward in significant resistance increase of the small patches way and metal layers as shown in figure. The metal layers are higher in stack or often ported from the prior technology for those upper metals. The wire resistor capacitor delay is reduced at the same rate as the designing area significant resistance cost. Current process technology typically use copper interconnect with a barrier layer that separates the copper from the surrounding silicon. As the width of those metals is reduced, the barrier layer, which is highly resistive become a larger greater than the width scaling as shown in figure, that results in a lower metal wire delay, which represents our more significantly delay compartment and shifts the overall wire delay layer sensitivity lower in the metal stack. Due to that shift, standard wire engineering techniques for a wire dominated critical paths which previously succeeded through the use of higher quality routes further up the stack, and also non-full routes lower in the stack have become less effective. While using NDR in the critical lower metal layer would be beneficial due to the process complexity at very small geometries, the technology has significant restraints with regarding to any use of nominee with width or spacing. This interaction between technology limitation and designing requirements is a good example of the importance of early upfront collaboration to come to an optimized solution. Another options to reduce the resistance impact is the use of new material. Cobalt is being introduced at the 10 nanometers node as a copper replacement for the small patch metals. While cobalt has higher natural resistivity than copper, it does not require a barrier layer and therefore has a lower resistance per unit length. Very tight widths. Cobalt also has the benefits of improved electromagnetisation, which also has the benefits which could still has a concern of copper wires, particularly 0, 20, 40, 60, so on. Up to 2020, Google search results the DTCO figure. The trends in DTCO papers, wire resistance, wire RC delay technology, node scaling, the estimated trends. This is the topic. The wire resistance between the lowest layer is a significant concern as we continue to scale dimension to even smaller values. Standard cell design. Standard cell development evolves with an influence technology. While standard cells must follow the technology definition, they are integral sources of early design feedback that can influence changes. Early design technology co-optimization is needed to identify the significant design complications so that the technology can be adjusted to mitigate the issue. An example could be the early layout, layout effect and a critical combinational and sequential cell where the standard cell team is finding a particular designing rule that is hindering the cell density or routability. The standard cell team can provide the feedback to the relaxed to improve cell scalability. That early feedback is crucial development technology frequency. Foundries and designers may have different ways to evaluate frequency benefits. A few of new process technology, often a set of cells, is simulated as a ring oscillator using a space and compared between new and older technologies to determine the process intensity. The cell that are chosen, and the cell fan out as accumulation may lead to different conclusion. Finding a reasonable number of cells that correlates to the actual design is helpful for making some initial frequency assumption. Once the initial frequency has been established through a ring oscillator simulation, the actual design can it be run by sweeping frequency around the target frequency. Thus, it can be determined whether the cell set from the ring oscillator correlate, and it can be understand whether the factor limit the design frequency. Root trial and fluorescent design. Comparing design with smaller set across different technology can provide insight into a different scaling assumption. Evaluating designing using different cells provides a variety of insight as well as designs are pushed to different frequencies. Different cells might be preferred by the synthesis tools. Comparing designing with similar cell sets across different technology can provide insight into different scaling assumption. Also, comparing large cell set contain can indicate which key cells might have an impact and improved design frequency. Larger cell may need a more robust routing from the cell level to the main routing metal layer, or for the other the electromagnetic migration rules for frequency target, especially especially due to the high resistance in the small pitch metals. Those viable connections may create a more placement constraint. Also, their additional routing resource requirement may impact the overall designing routing the frequency of the design. A route design would be required to evaluate the impact on the placement as well as the quality of the results. Finally, the implementation of real real design helps to the quantify some of the process technology implementation that are not easy to determine when making comparison at a cell level. This includes the overhead for the well tapped cells, considering the area impact of well tapped cell size and the well tapped cell density for latch up prevention. Another example for single various double diffusion breaks overhead, which may impact the area of some cells, how the cells can be about, uh, and how the aptitude cells are interact with power grid. The final example is the contact over a grade construction enables more routing flexibility. Figure illustrate the density using real design for a previous. Thank you.